Okay, so let's do one example from the gas mixture. So in this example, we have a rigid tank, and in this tank we have two gases. We have oxygen and we have carbon monoxide, CO2, and the number of moles for each gas is given here. The question is asking for the volume of the tank based on different methods. So what we want to find what is the volume that holds this mixture within the tank. Now in part A, the question is asking to do that based on the ideal gas law. So the ideal gas law is pretty simple. Basically, it says the pressure of the mixture multiplied by the specific volume of the mixture is equal to the number of moles. Actually, because what I'm going to do, because I'm going to use RU on the right hand side, so let's say this is going to be directly the volume, not the specific volume. So once again, pressure of the mixture, volume of the mixture, number of moles, RU, which is the universal gas constant, and the temperature of the mixture. Okay, so all subscripts M are for the mixture basically. Pressure, volume, number of moles, the universal gas constant, which is a fixed number, and the temperature of the mixture. Okay, so the pressure is given in the problem statement. So that is 10 megapascal. If I want to end up with the volume in meter cube, I need to convert that into kPa. So basically that gives me 10,000 kPa is my pressure. Volume of the mixture is what I'm looking for, is equal to Nm is the number of moles, okay, and that simply comes by adding a 3 kilomole and 4 kilomole. So Nm is number of moles. So for number of moles I have 7 kilomole, and my Ru is a fixed number, 8.314 kilojoule per kilomole Kelvin. So once again, I mentioned that previously, but this number comes from table A1 of your textbook. And finally, Tm is the mixture temperature. Okay, and the problem statement gives me the Tm, the mixture temperature as well, multiplied by 350 Kelvin. So the only unknown in this equation is the volume of the mixture, so you can find it and obtain it. And by the way, this 7 kilomole is obviously coming from 3 kilomole plus 4 kilomole. So 3 plus 4 kilomole. So if you do the math, you will obtain volume of the tank equal to 2.036 meter cube. So that is answer for part A. So based on ideal gas, I got 2.036 meter cube. Now in part B, the question is asking to do that based on the K's rule. Okay, now we learned about K's rule in a previous video. What we are doing in K's rule, we are looking at the mixture as a pseudo-pure substance. We are assuming that instead of like different components or different gases, we just have one gas that has the critical pressure of P prime critical pressure and the critical temperature of T prime critical temperature. All right, so basically instead of dealing with different critical pressures and different critical temperatures for each component, I'm getting the average of that with mole fraction. So this yi is mole fraction, this yi is the mole fraction. So I'm going to use this equation to obtain the critical pressure and the critical temperature of the mixture. Okay, so in order to do that, the very first step for me in part B is to obtain the mole fraction of each component. So let's say I have oxygen and I have CO2. The mole fraction of oxygen is going to be the number of moles that I have in oxygen over the number of moles that I have in the mixture. Okay, for oxygen I have 3 kilomole, and for mixture I have 7 kilomole. Okay, and that gives me a mole fraction of 0.428. I do the same thing for CO2. So the mole fraction for CO2 is the number of moles that I have in carbon monoxide over the number of moles that I have in the mixture. Okay, so for carbon monoxide I have 4 kilomole, and in the mixture we have 7 kilomole. And that gives me a mole fraction of 0.571. Okay, now the next step is me obtaining the critical temperature of the mixture. So that is T prime critical M, which is obtained by mole fraction, or the sum of mole fraction multiplied by the critical temperature of each of the components. So this requires me to obtain the critical temperature of each of the components that I have. So let's say starting with oxygen, my Yi for oxygen is 0.428, and I go to the table, I obtained the critical temperature for oxygen, and that is 154.8 Kelvin, plus I do the same thing for the other component that I have. So it's going to be 0.571 multiplied by the critical temperature of CO2, and that is 304.2 Kelvin. So the answer is 239.9 Kelvin. Okay, so this number, in case you're asking where is what is this number, this is T critical of oxygen, and likewise this one is T critical of CO2, and this is the mole fraction of oxygen, and this is the mole fraction of CO2. Okay, now my pseudo pure substance, you can call it whatever you want, has the critical temperature of 239.9 Kelvin. I do the same thing for the pressure. So that means my pseudo pure substance will have a critical pressure of sigma YIP critical of each of the components. All right. So once again, for oxygen, YI is 0.428. The critical pressure of oxygen from the table is 5.08 megapascal, plus the mole fraction for CO2 is 0.571 multiplied by the critical pressure for CO2, which comes again from the table, 7.39 megapascal. All right, so that gives me the critical pressure for the mixture equal to 6.393 megapascal. Okay, so once again, this number is P critical of oxygen, and likewise this one is P critical of CO2. All right, now I have a substance, I have a gas which has the critical temperature of this much and has the critical pressure of this much. Okay, so I know the critical values. What I'm going to do right now, I'm going to obtain the reduced temperature and the reduced pressure based on the critical temperatures. Okay, I'm going to utilize these two numbers to obtain the critical properties. So let's say I'm looking for instance, TR, which is the reduced temperature, is the temperature of the mixture divided by the critical temperature of the mixture. Okay, the temperature of the mixture is given in the problem statement, and that is 350 Kelvin. Now the critical temperature of the mixture is what I've obtained here, so that will be 239.9 Kelvin, and the answer is going to be 1.45. So my case in this problem, or my state in this problem, has a reduced temperature of 1.45. I do the same calculation but for pressure. So the reduced pressure is equal to the pressure of the mixture over the critical pressure of the mixture. Okay, so the pressure of the mixture in the problem statement is given at 10 megapascal. The critical temperature is obtained at 6.393 megapascal. and the critical pressure is 1.564. Now what I would do, I would use these two numbers and I go to figure A15, and based on that I would read the Z value. So Z is going to be 0.85, and this Z comes from figure A15. Okay, now what is Z? Z is the compressibility factor that we had in the real gas law. So basically previously we had pressure multiplied by volume is equal to Z, number of moles, RU, universal gas constant, and temperature. Okay, pressure, volume, compressibility factor, number of moles, universal gas constant, and temperature. But here is what I need to include: the pressure of the mixture, the temperature of the mixture, okay, and the number of moles in the mixture that I have. And obviously if I solve this, I'm able to obtain this volume. So this is known, this is known, this is known, this is known, this I just obtained this Z. So I did all this story to obtain the Z value. So based on that I can find the V value, which is the volume of the mixture. So just putting in the numbers. For pressure of the mixture I have 10 megapascal, and you know what, I need to convert that into kPa. So let's say 10,000 kPa multiplied by the volume of the mixture is equal to Z, Z being 0.85, it's a dimensionless number, multiplied by the number of moles in the mixture. I have 7 kilomole, multiplied by RU, universal gas constant, 8.314 kilojoule per kilomole Kelvin, and Tm is the temperature of the mixture. Make sure that your unit for temperature is in Kelvin. So by solving this, you will obtain the volume of the mixture, and that is equal to 1.73 meter cube. So this is the volume of the mixture based on the K's rule. So if I get back into this table, initially by using the ideal gas law I had 2.03. Now by K's rule I have 1.73 meter cube. So you can see the difference between them. Now in part C, the question is asking for the compressibility factor and Amagat's law. Okay, so we discussed about Amagat's law earlier. In Amagat's law, what we are doing, we are obtaining the Z for mixture, okay, based on pretty much the same approach that we did for the critical values, but this time in Amagat's law, the Zi, or the compressibility factor for each gas, is evaluated at the temperature of the mixture and the pressure of the mixture. Okay, now this is in contrast to Dalton's law. In Dalton's law, we obtain Zi, or the compressibility factor for each component, at temperature of the mixture and at the volume of the mixture. But in Amagat's law, we are evaluating the Z's at the temperature and the pressure of the mixture. So let's do that. So what I'm going to do, I'm going to obtain the Z value, actually two Z values, one for oxygen and one for CO2. And then once I have that, I'm going to utilize this equation to obtain Zm, which is Z for the mixture. All right, so this is part C that I'm trying to solve. So in part C, for oxygen, I have the reduced temperature of oxygen over the critical temperature of oxygen, and that's going to be 350 Kelvin over 154.8 Kelvin. That gives me a reduced temperature of 2.26 for oxygen. Why am I doing this? My goal is to find Z value for oxygen and also do the same thing for CO2. So I'm going to have two separate Z values. The reduced pressure for oxygen is going to be the pressure of oxygen over the critical pressure of oxygen. So the pressure here is 10 megapascal and the reduced pressure is 6.393 megapascal, and that gives me a reduced pressure of 1.564. Okay, now I will use these two values, these two reduced properties, to obtain Z value. Okay, once again, you're going to A15, figure A15, and you will obtain the Z value, which is equal to 0.97. Okay, now exactly doing the same thing, but this time for CO2. So the reduced temperature is temperature of CO2 over the critical temperature of CO2. The temperature as well as the pressures are the same, so 350 Kelvin, only this thing changes. It will be 304.2 Kelvin, and that gives me 1.15 for the reduced temperature. For reduced pressure, I will have P of CO2 over the critical pressure of CO2. The pressure is 10 megapascal, and the critical pressure is 7.39 megapascal. So if I solve that, that is my reduced pressure. Now, once again, using these two values, I go to A15 and obtain Z for CO2, and that is 0.66. So let me, by the way, add the subscript. So this is Z for CO2, and this was Z for O2, and this is also coming from A15. My next step is, let me once again show you this page. So this is what I've done so far. So far for the Amagat's law, I obtained Zi, I is for each of the components based on the temperature of the mixture as well as the pressure of the mixture. Okay, now I have two Zi values. I'm going to obtain Zm, which is the Z for the mixture, based on this correlation. This is the mole fraction and this is the Zi value that I obtained. So my Zm, Z for mixture, is going to be sum of Yi, Zi. Okay, so for oxygen, my mole fraction is 0.428, and my Z for oxygen is 0.97, it's right here, plus my mole fraction for CO2 was 0.571 multiplied by my Z for CO2 is 0.66, and that gives me Zm, or Z for mixture, equal to 0.792. Okay, so this is Y of oxygen, this is Y of CO2, and you know Y is the mole fraction, so we did it at the very beginning of this problem. So if I go back to the first page, you see that we already obtained Y values here. So these are the numbers that I'm using. Okay, so now I have Zm. All I need to do is use the same equation. The pressure of the mixture, the volume of the mixture is equal to Zm, number of moles in the mixture, Ru, temperature of the mixture. Okay, so pressure, I have it. Zm is what I just obtained. So this is equal to 0.792. Number of moles is 7 kilomole. Ru is 8.314 kilojoule per kilogram Kelvin. And Tm is the temperature of the mixture. So I have all properties except Vm. If you put the numbers, you will obtain Vm equal to 1.612 meter cube. Okay, so if I go back to the previous page, I can add these numbers so we can have all of them side by side. 1.61 meter cube. So all of these numbers are the same property. They are the calculated volume of the mixture, and you can see the difference between them. The ideal gas law gave me 2 point something, the K's rule gave me 1.7, and the Amagat's law gave me 1.6.